So, a very good afternoon, participants, and respected Dr. Suwarna Datar ma'am, Dr. Suved Lemon ma'am, and all dear participants. I welcome you all for AICT Atal Academy sponsored 1-week online faculty development program on photonics, active learning in optics and photonics, organized by Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur. Today, we have a very distinguished personality, Dr. Suwarna Datar ma'am from Defense Institute of Advanced Technology, Pune, which comes under Ministry of Defense, Government of India. Madam completed her BSc from SP College, Pune, MSc from Ferguson College, and PhD from Savitribai Phule Pune University, Pune, on the topic Investigations of Structured Materials using Scanning Tunneling Microscopy, Spectroscopy, and related techniques. Immediately after that, during her research, she has earned expertise in investigation of nanostructures using scanning probe microscopy and well versed with techniques of nano deposition and nanoparticle synthesis. She has worked on home built and commercial scanning tunneling microscope. As participants, as we know, the cost of scanning tunneling microscope is very high, and she has worked on the home built and commercial both machines of scanning tunneling microscopy. She has experience on developing scanning probe microscopy tools involved in. She is involved in development of dynamic mode atomic force microscope. Presently, her research is on applications of graphene nanoribbon for EMI shielding, steel chemical sensors based on tuning fork, biomedical applications of metal nanostructures. She is along with assistant professor at Defense Institute of Advanced Technology. She is a principal investigator of DIAT DRDO program on nanomaterials. Madam at her institute has a MTech program in optoelectronics, and in that she is guiding MTech and PhD students for their thesis. She has more than 50 publications in international journals, conference proceedings, and book chapters. She has been invited for several international conferences, seminars, workshops, and she has guided around 30 students for their MTech dissertation and 6 PhD students. She is a reviewer for several international journals, awarded certificate from Institute of Physics as one of the top cited researcher from India in 2019 for a publication EMI shielding materials in Journal of Nanotechnology. Such a wonderful personality we have with us. She's going to talk on the blue sky and red sunset. I welcome you, ma'am, to this faculty development program and request you to start your presentation. Thank you, ma'am.
Yeah. Thank you, sir. Nice to see you, and thanks a lot for giving this opportunity to me. I would have preferred a topic which was a little bit advanced because this is very difficult to teach. I remember Suwad taking this part and online. So I referred to all the notes which we had taken and uh, the experiments which we performed there. So, and then I thought I'll show a few experiments. Let us see if I can show them, and then I will start with the presentation. Okay. So let me share the presentation and. Yeah. There is a present share. No? Yeah. So I tried to find those beads also, which I couldn't find. So
Okay.
Anyway, so you can see the presentation now.
Now it is coming. Yes, it's
now.
Yes.
Yeah.
Yes.
Okay. So in this presentation, what I'm trying to do is I'll show you very few slides, and then I'll show the experiments which we did during the course, which we did in 2000 early this year, I think, and no, last year same time. And then I'll try to see the way we were taught is that there were some questions which we were asked after showing these experiments, and we were supposed to figure out what the answer would be. So let me clarify that I am like you all, and I'll to repeat what was done during that time. Only thing is, since we cannot do the hands-on here, I will try to compensate that with some mathematical explanation about what is happening. So that's why I need two devices. The other one I will use uh, for deriving some few things which will tell you about the scattering. You all probably are, of course, aware of the scattering of light, and there are three things which can happen depending on what is the size of the scatterer. If the size of the scatterer is pretty large, let us say for a raindrop of 10 to 100 microns, then you will see all the colors which are scattered, and so you basically see white light. Okay. Then if you have aerosols, slightly smaller particles which are of the order of same as the visible light wavelength, then it's a different phenomenon which we are not going to discuss about. And the last part, which is the topic of this presentation, which is Rayleigh scattering, when the scatterer molecules are very, very small, and they cause this blue sky and red sunsets. So here is the size of the, it's the same slide which tells you which type of particle will show what type of scattering. Okay, so let me show you some of the experiments which we did. So what we had done, is this visible to you? Yes, right?
Yes,
So
yes,
what
ma'am.
we had done, yeah, during our course is that we shine a light on this like this, right? And we don't see any different color. It's done. So we used to predict. So what color is this? So it was kind of transparent. Now, if I put a few drops of milk in this and stir it properly, very few drops you need. I think I got a bad milk. And then you see the color. I don't think in camera it's showing.
Yeah, it is seen. Hmm.
It is seen. So, so you will see that at the bottom, I could see a blue color, while at the top it was almost yellow and reddish. And
Yes.
as I increase the concentration of water droplets, it will also increase. Same you can do with bubbles of soap water. So if you see the bubbles which are very close to each other at the bottom, they are white in color. On the other hand, single bubbles, if I see, they will show some different colors. So these experiments you can do for your students and check for yourself. Unfortunately, we cannot do them here. So first we show that using uh, a grating or some spectrometer, that white light is made up of different colors, and then we can move on to these experiments. So while I cannot perform those experiments here, I can of course explain to you why all this is happening. Why do we see blue sky? Under what circumstances do we see blue sky? Under what circumstances we see sunsets, which are so wherever we are standing, depending on that, depending on the angle, how it changes. So let me share again with you the uh, slides. Okay. Okay. So, can you see my
Screen,
slides
yes.
here?
Yes.
Screen you can see. Okay. So it all starts with Maxwell's equation. Okay. So the four Maxwell's equation which we talk about are so del dot E is equal to rho by E epsilon 0, right? The Gauss's law, that is the divergence of E. Since there are no charge carriers in vacuum, we can say del dot E is equal to 0, right? Then del dot B is equal to 0 is another Maxwell's equation. Uh, then the curl equation, which is del cross E, is equal to minus d by v by d by t, which is the Faraday's law, and del cross B is equal to mu 0 j plus epsilon 0 mu 0 d by e by d by t. So the last equation, the first term will is nothing but the Ampere's law, and Maxwell added the second term, which gave rise to several of the properties which we now know. Okay, so my electromagnetic waves, which we talk about. So how do we get the wave equation? Is we all know about this. So we take a cross product del cross E. So and we use the identity that uh, del cross any vector A will be del dot A minus del square A, right? The same identity, if I use it here, then I will get del cross E is equal to minus d by dt of del cross B. Another thing while doing the experiment which we did was we saw the scattered blue light, and when we see it through a polarizer, the scattered blue light at a particular angle is polarized. So the things which we would like to understand from whatever mathematics I'm telling you right now are the following. One is why the sky is blue, of course, and when we are closer to the sun, do we see sunsets red? Why are clouds white in color? And uh, the scattered light, if I see through a polarizer, then I can see that it is actually polarized. Okay.
Ma'am, you are not audible. Dear participants, ma'am may be having some issue related to connectivity. She will join by that time. Please stay tuned.
Dr. Yadav?
Yes, ma'am.
Can I ask a question?
Yes, sure.
Are the universities in your country open or closed now because of COVID?
We are work from home, ma'am.
From home, same thing for us, yes.
Yes.
And when we are just starting, so we have so many problems with connections and so on.
Yes.
Even teachers and students, all of us have problems, but
Yes.
we have to do.
Earlier we were using Zoom, but government has banned Zoom app. So we have to use Microsoft Teams app, and it requires a lot of bandwidth.
Okay. Okay,
So
Suwarna is back now. Let's.
Yes.
Thank you. Thank you.
Yes.
Suwarna, we don't hear you.
Unmute yourself, ma'am.
Yeah. Am I now audible?
Yes.
Yeah.
Yes.
Okay. And is my screen visible?
Your screen is not visible.
Not yet.
My screen is visible or no?
No, not visible.
Due to am I still audible or not?
Or you are audible, ma'am. You are audible, also visible, but screen is not visible.
Screen is not visible. Okay. Due to you are not in a call or meeting starts. Okay. Yeah, I have joined from another device.
Yes. Reduce its volume.
Echo is there? Yes. Now I think this should be fine.
No echo, ma'am, now.
Yeah, no echo now, right? Okay, sorry about that. Yes.
Your screen is also visible.
Okay.
Yeah.
Okay, we are good.
Yes, ma'am.
So
Please
far.
Yes.
Okay. Fine. So I don't know where it stopped. I kept on talking. So let me repeat few things again.
Yes.
Yeah. So what we want to understand from whatever mathematics I am going to tell you are the following things. One is when we saw the light through water which had uh, particles of milk, we saw a blue color at the bottom, and from I had shined the light from the bottom, so the blue color was at the bottom, and above the one which was coming out was almost close to yellow red, like that. So it replicates what we see in the sky, kind of. So we see blue sky when the sun is above us, and as it goes to horizon and it sets, we see red sunsets. That is something which we would like to understand from the mathematics which I want to describe. When we did the experiments, we also saw the scattered beam through a polarizer, and we realized that at a particular angle, the light which gets scattered is polarized. So that is also we would like to see through these mathematical expressions. So the way I wanted to describe this is the way electromagnetism is taught to us. So we have Maxwell's equations. From Maxwell's equation, we arrive at wave equation, which gives us the velocity of light. So, like I said, if I take del cross E, I will get, I can write it as minus d by dt of B. So, del cross B. Since the first term, del dot E is equal to 0 in vacuum, I only get this expression, and the solution which I get will be del square E is equal to epsilon 0 mu 0 d2E by dt square. So which is the wave equation, famous wave equation, and it gives us the velocity of light. So since it's a wave equation, the first term which we get is velocity v, which is equal to 1 upon square root of epsilon 0 mu 0. And if we calculate this, it comes out to be 3 into 10 to the power 8 meters per second, which is the velocity of light, right? On the same lines, I can also derive an expression for del square of B, which is equal to mu 0 epsilon 0 d2E by d2V by dt square, right? So both of them together travel with the speed of light. We cannot separate them together, so that's why these they are electromagnetic waves. And what is the solution of these electromagnetic waves? So if I consider a wave traveling, if I consider an electric field which is in x direction, and I consider a right-handed system, then I'll get the solution Ex to be equal to E0x cos of omega t minus kz. Since Ey is equal to 0 and Ez is also equal to 0, right? So I can write the equation as if I want to derive this equation, del square E will reduce to just one term, which is d2Ex by dz square, which is equal to mu 0 epsilon 0 d2Ex by dt square, right? And del cross E, which is equal to this, right? So because we have only one term which is Ex in Z, and this is the final expression which we get. And the solution for this is a sinusoidal waveform, so which is equal to k into, yeah, just one. So del cross E I can write, let me write that also. Del cross E is equal to dia by Ex by dia by Z in Y direction, which is equal to minus dB by dt. Right? So this is the only term which survives when E is in X direction. So I can find that out by taking the derivative of this term, and I will get K into E 0x sine omega t minus kz, which is in Y direction, which is equal to minus dB by dt. Okay, so similarly, I can find what is by, right? So by will also be equal to, from here only, if I integrate this term, I will get the expression for magnetic vector B, which will be equal to E0x cos of, the minus sign will go, it will be minus cos, but both, so I can write it as cos of omega t minus kz into y, right? So here we will have divide by c. So associated with each ex, which we are going to have by, and if you look at the magnitudes of E and B, then magnitude of B is smaller than E by smaller than E by C times. B C times smaller than E. And so what are the properties of these plane waves? E and B are perpendicular to each other. They are perpendicular to the direction of propagation, right? So the way we explain it, so if I draw them at a particular freezed time, they will look like this, right? So you have X, Z, and Y direction, and the sinusoidal waveform or cos. So you have E vector like this. Then you have B vector like this. In Y direction, right? So they travel in forward direction with the velocity of c, right? So this was a plane wave only in x direction. If I had a plane wave, say in both directions, x and y, so if I write, so, and they are independent two plane waves, one in x direction, one in y direction. So I can write the expression for such a plane wave like this. So E is equal to E0x first term cos of omega t minus kz x prime in x direction, and I have EOY into cos of omega t minus kz plus delta. I have a phase, also phase difference also in y direction. Okay, so if I have a wave like this, then how do I get? So this is my x direction and sorry, y and x, and I have, so let us say delta is equal to 0. Then whenever I have maximum here at EOX, so this is the maximum in x direction I'm getting. At the same time, I'm also going to get maximum in y direction, right? So if I do the find a vector sum of these two vectors. So total E will be equal to square root of EOX square plus EOY square. So in this direction, right? So I still have so this is the way we started. We had electric field only in x direction, so it was obviously linearly polarized. Now, if I have such a vector, even then it is linearly polarized, not in x direction, but in this particular direction, which is a linear combination of two waves, right? Now, if I have delta is equal to pi by 2, then whenever I have x maximum, so I have EOX here, I will have pi by 2 phase difference to EOY is going to be 0. And whenever I have EOY positive maximum, I will have EOX equal to 0, the same way here in this direction, same way in this direction. And therefore, it follows a path of an ellipse. So this is elliptically polarized wave, right? If the dimension magnitude of EOX and EOY was same, then I would have got a circularly polarized. So we could have seen all this polarizations using actual polarizers. I didn't know how to do that here. Okay. Now, what about the light which comes from sunlight or tube light? It is unpolarized light. So what do we mean by unpolarized light? So if we consider a point and it has a photon which is falling on it, which is linearly polarized in this direction. Another one comes which is linearly polarized in another direction. Third one comes which is linearly polarized in another direction, and like that. If we keep doing this, then there is no specific polarization of light in this particular point. And that's what happens in case of sunlight or in case of the tube light which we see. So it is an unpolarized light. Okay. So now having understood what is polarization and wave equation, what is the energy stored in an electric field? So you would recollect probably from our when school studies, the energy in an energy density in an electric field is half epsilon 0 into E square. Similarly, in B is half half B square by mu 0. Okay. Now you have a traveling electromagnetic waves, and we know that magnitude of B is equal to magnitude of E by C, right? And therefore, I can also write energy density in a magnetic field mu B to be equal to E square divided by 2 mu 0 into C square, right, from this equation. And but E square by 2 C square, I can write this as epsilon 0. So I can write 1/2 of epsilon 0 E square, which is nothing but mu E, right? So basically, energy density of electric and magnetic field is same. Obviously, because they are moving in the same direction, moving together, and therefore I can write the total energy to be equal to epsilon 0 E square. Okay, or I can also write this as epsilon 0 E B into C in vacuum, of course. Okay, so I don't know if I should be telling you, you would remember this, what is Malu's law, but probably I'll once again tell you. So what does a polarizer do? If I have a polarizer like this and a photon of a plane wave, uh, a plane electromagnetic waves is passed through it, you have this polarizer like this, then what it does is it reduces the intensity. So if I take a projection of this, since it's going to turn it into a particular direction, and therefore this E0 becomes E0 cos theta. Okay. Pointing vector, which we will again talk about, is the direction of energy vector. So we'll talk about that. Is so if we have all the photons which fall on this particular point, then the mean value of this is actually, since cos square theta mean is going to be equal to 1/2, and therefore the intensity goes to half of the input intensity, or the intensity is reduced by cos theta, and this is known as Malu's law. Okay, so if I want to understand what is the energy flow from a particular area perpendicular to the direction of propagation. So suppose if I have this 1 meter square area from which electromagnetic waves are going out of that with a velocity of c. This area is 1 meter square. Then how much is the radiation coming out in 1 second? Okay, so if I want to calculate that, so if you joules per second meter square, okay, is the energy per meter, energy density per meter square, or I can write watt per meter square. This will be equal to total energy multiplied by C. So this total is nothing but epsilon 0 E B into, so now multiplied by C, so C square. Or I can write this as E into B divided by mu 0 also, which is nothing but our pointing vector, which we talk about, right? So S, which is equal to E into B by E cross B into mu 0. E and B are perpendicular to each other, right? So this is watt per meter square. So now if I have E, which is equal to E0 cos omega t, and I have B, which is equal to B0 cos omega t, and pointing vector, the average of cos square omega t will be equal to half, and therefore average of pointing vector will be equal to half epsilon 0 b, sorry, not epsilon 0, E0 B0 by mu 0, right? Or I can write this as half E0 square by mu 0 C, because B is nothing but E0 by C. So if we know the strength of electric vector, then we can calculate the pointing vector, right? And so if the strength of electric vector was 100 volt per meter, Then the pointing vector I can calculate by 100 square divided by 2 into mu 0 c, and I'll get some number. Similarly, I can calculate how much is the energy which we receive from sun. Okay, so if I have a sun which has energy of 3.9 into 10 to the power 26 watt, right? It is going to reach a sun reach the earth. So if I consider 1 meter square area, the distance is 150 million kilometers. So around this radius of 150 million square meter, how much is the pointing vector, or how much is the energy or watts per meter square which we receive from sun? So this comes out to be equal to 1.4 kilowatt of per meter square, which is known as the solar constant, right? And so how do I calculate? So actually I cannot create an electromagnetic field from the solar light and calculate it. So the way the electromagnetic field is created is by accelerating the charge. So unless we accelerate a charge, I will not create a electromagnetic field. Okay, and so if I suppose I have a charge at this point and I accelerate this charge with some acceleration, and therefore it moves to say another point, say mu prime, 0 prime, and then it moves with a constant velocity up to this. Okay, so at what will be the so this is a charge, positive charge q at this position O, which is at rest. I accelerate in this direction, so a, with acceleration a, for time say delta t. So it reaches O prime. Okay, now it attains a velocity which is, let us call it u, which is also in this direction, and the velocity will be equal to how much? Acceleration into delta t. Right? At t, suppose at time t, it is at this point O double prime. Okay, so it moves from t, so t plus delta t is the time taken by this charge particle to move from O to O double prime, right? So I can draw this sphere around it. So suppose I have this point O, I have O prime and O double prime, and so I will draw this sphere around O with radius r. Okay, so let us say this is the radius. What will be the dimension of r? R will be equal to, at O, if O was the radius, then R will be equal to the velocity of light into t plus delta t. Right? After it reaches O prime, it moves with the constant velocity u. Right? So I will be able to draw another sphere with which has a radius of c into t, right? At time t, it's going to reach this point. So we have another radius like this, right? So if I just draw this projections here, okay, now this r is equal to c into t. Okay, so this is u perpendicular component of this distance will be perpendicular component of u into time. Then this distance is going to be c delta t, right? The wave is propagating in this direction. So my E, this is going to be E parallel, and this is going to be my E perpendicular. Okay, so the electric field inside this shell is responsible for the radiation. How do I get the radiation? Only when we accelerate the charge. Okay, so that is only inside this shell. And since E perpendicular component is perpendicular to the direction of propagation, that is going to represent the energy which is flowing out. So if I take the ratio of E parallel and E perpendicular, this E parallel will be same as C delta. In just 1 minute. Yeah. So this will be same as U perpendicular into T, and this will be same as sorry. I will take the ratio of E perpendicular divided by E parallel. So this will be same as UT into T into C delta T. Okay. So the velocity with which the charged particle is going to move will be equal to acceleration into delta t. So u perpendicular will be also acceleration in perpendicular direction into delta t. Okay, and so I can write this ratio E perpendicular divided by E parallel equal to A perpendicular delta T into T divided by C delta T, which is equal to A perpendicular T by C. Okay, T I can replace by R by C. So I can write this as E by E parallel equal to A perpendicular R by C square, or A perpendicular, E perpendicular is equal to E parallel into A perpendicular R by C square. Finally, we want to know what is going to be the electric field which is radiating out. So how do I find this? We can use the Gauss law. And so if this is E, which is going in vacuum, whose divergence is going to be 0 because it's in vacuum, then using, so this is my E parallel component. These two are E perpendicular components. So since in vacuum there is no charge density, your divergence is equal to 0. And we know from basic electromagnetics that this E, electric field E, is equal to, at a distance of R, is equal to 4 pi epsilon 0 R square. So same will be E parallel also. And therefore, I can write E perpendicular to be equal to A perpendicular divided by C square, Q divided by 4 pi epsilon 0. Here you have R square, so it is 1 by R. So if you compare this with the static electric field strength, you will see that we have 1 by R. So electric field falls as 1 by R square in case of static electric field. On the other hand, this traveling wave, electromagnetic traveling wave, has electric field which is falling as 1 by R. Okay, so I can write E RT, which is equal to minus A perpendicular. Minus sign comes because the charge is positive, and so the electric field vector is going to be in the opposite direction. Okay, so it reaches our eye at some point of time. So function of t divided by c square 4 pi epsilon 0 r. Okay. Now, once I get this, like we discussed, we can also get what is the vector B, and we can also get what is the pointing vector S, right? And so, if I just plot acceleration A and vector R, this is the angle theta, okay? This is the perpendicular component which we are concerned with. So A perpendicular. So this A perpendicular is going to be A sine theta, right? And therefore this E vector is also proportional to A sine theta. And therefore pointing vector S is proportional to sine square of theta, right? And therefore the spherical waves which are going to go in different directions will depend on the angle, and because the pointing vector is going to be different in different directions. Okay, so the amount of energy per second which flows out of per square meter in a plane perpendicular to the acceleration. So whenever you have energy which is flowing out from a plane which is perpendicular to the acceleration, it is very, very high. And as we move from a perpendicular plane, the plane in which the acceleration is there, the energy is zero. Okay. So it's going to change everywhere, right? So from all the mathematics which we did, the few observations which we can probably remember and forget about is that we need acceleration to get an electric field. Then accelerated charge in a direction, say A, at some point R, you are going to observe an electromagnetic waves, and E is going to be in the same plane as R and A. That is one thing. Also, E is perpendicular to R because that's the wave traveling. Mod of E is proportional to perpendicular component of acceleration. It is positive if the charge is negative, it is negative if the charge is positive. And mod of E is proportional to 1 by R naught, 1 by R square, right? And of course, pointing vector is proportional to E square. So from all the mathematics which we did, this is what we take away from that. And then now if I have a big sphere, then I have to average out all these pointing vectors. So total power, if I calculate, which is produced from the electromagnetic wave which is oscillating, then we have to integrate this pointing vector in the entire sphere, and the expression which you get from there is, so this is the expression we needed for the discussion: q square a square divided by 6 pi epsilon 0 cq. basically we want, this power is not per unit volume, but it is in watts. And so this power is proportional to amplitude square. So how much is the energy flow per second through a sphere? If I want to find out, then it takes energy to first of all accelerate a charge, and so it takes energy to create electromagnetic field due to the motion of charge. And so now with this information of how much is the power which is associated with electromagnetic waves, if I now consider a single charge, a bound charge on which a linearly polarized light is falling on it. Okay, so we have a linearly polarized traveling wave which is come on this charge Q. This is a bound charge. Okay, since it's a bound charge, when this wave hits this charge, there is going to be some restoring force which is going to hold this charge, and therefore it is going to oscillate with certain frequency. What will be the force which is experienced by the bound charge? So F I can write is Q into E, so which is equal to E0 cos omega, right? Because of the Coulomb interaction, there is going to be a restoring force, and the charge is going to oscillate with certain frequency. We'll call it its resonance frequency omega 0, which will be equal to K by M, where K is the force constant, right? If we assume that there is no damping, then I can write a differential equation for this of forced oscillation. Okay, so what are the forced oscillation? You have an acceleration, which is x double dot. Then you have this restoring force, which is equal to omega 0 square x, and force applied is this much. So I can write this equation as x double dot plus omega 0 x equal to q epsilon 0 cos of omega t by m. So I removed m from both this and brought it here. If I solve this equation, we know the solution. We will get x to be equal to a cos omega t, and the amplitude of oscillation of this electron A will be equal to q by m into q by m into epsilon 0 divided by omega 0 square minus omega square. Okay, so I can now substitute the value of x and a and substitute that and find out what is the acceleration, which is our interest. Okay, so acceleration, if I take the double derivative of this term, what I will get is x double dot is equal to minus omega square x. You can do that. X dot is equal to a omega sine omega t. Then x double dot is equal to minus a omega square cos omega t, right? So x double dot is equal to this, and so I can write this as acceleration A will be equal to minus q into E0 omega square cos omega t divided by m into omega 0 square minus omega square. Okay, so and from the expression for power, we know that the power that goes into the field, or the if I have a rate electron is radiating electromagnetic waves, then that power is going to be proportional to a square, and we will leave all the terms, other terms, and we'll just focus on frequency component. Then this power is proportional to omega raised to 4 divided by omega 0 square minus omega square bracket square. Okay. What happens is this resonant frequency. So suppose if I have omega, which is much smaller, the frequency which is falling on falling is much smaller than omega 0, the resonance frequency, then this power is going to be proportional to omega 1 by omega raised to 4. Okay, and that is what is Rayleigh scattering is. Okay, so the radiation that comes in has a, suppose the radiation which is coming in has a frequency which is omega, then what comes out, first of all, the frequency, input frequency is also omega, the output frequency is also omega, so there is no change in frequency but only in direction, and therefore it is scattering. Okay, so what happens in atmosphere is that you have oxygen and nitrogen molecules, and their resonant frequency and resonant frequency of several other particles is pretty large than the frequency of visible light. It's in far UV range, and therefore this power is proportional to omega raised to 4. And since blue has a highest frequency, blue light has much higher probability to scatter, uh, to get scattered by a moving particle than a red light. Okay, so if I take the entire range of red and blue, then omega of blue, and take the ratio omega blue by omega red, it comes out to be equal to 1.5. And I take fourth power of this, so we get 5 times more probability of scattering of blue than scattering of red. Okay, so though this is true when particles are much smaller than the wavelength of light, if the particles are get bigger and bigger, then you will see that it becomes white. So all the colors are going to get scattered, and so you see a white color. Okay, so let me stop this share and let me share with you the presentation which I was showing you. Okay. And I would like you to ask, if you want to ask any questions, you can ask. Okay. Let me just share my presentation. Yeah. So now probably we will be able to answer these questions which we had written. So when there is a cloud, the cloud has lot of water molecules, and so they are much bigger than the wavelength of light which is falling on it, and therefore all the colors get scattered from the cloud, and we see, so whenever we have a cloud formation, we see them as white. On the other hand, when there is no cloud, we see that the sky looks blue. Okay, then yeah, so when depending on where we stand, so the angle at which it reaches, light reaches us, so when we are here, we see blue sky because the scattered waves mostly are blue. But when we are at the sunrise or sunset at the horizon, we are at an angle such that all the blue light gets scattered away, and the only light which reaches us finally is the red light. Okay, and so we see orange or red sunsets. These are the questions which now, after this, we should be we should try to explain. Uh, so we have Rayleigh scattering from the air molecules, because of which we have blue skies and red sunsets. Same expressions I have shown here. Okay, now these are some of the questions which I would have put before we discussed about the mathematics part of it. However, this is how I could show. Okay, so if you have any questions related to this, you can ask me. This is not my topic of research, but I tried to see how one can teach this topic of sunrise and sunset to people like you who are already teaching for several years. Okay, so I hope I made some sense while I discussed it. So if you have any questions, you can ask.
Thank you, ma'am. Thank you, ma'am. Participants, madam has given a wonderful lecture about the blue sky and red sunset and sunrise. The session is open for discussion. If you have questions, you can raise your hands, else you can unmute yourself and ask your questions. Neha ma'am has raised her hand. Neha ma'am, please unmute yourself and ask your question.
Good afternoon, ma'am. The session was very beautiful. You explained so many things so well. Ma'am, one question is there. Ma'am, as you explained
Yes.
about white cloud, my question
Yes.
is that what is the reason for colorful clouds?
Colorful meaning red sometimes.
Yes, ma'am. Yes, ma'am.
So mostly there are particles which are stuck there, which are smaller in size than the wavelength which is falling on it, and therefore they scatter different lights than white light. So they will scatter blue more, and what reaches us finally is uh, what remains after scattering all other lights. Whatever remains is what reaches us, depending on the angle at which we are standing. So you would probably remember eclipse time when I think we had seen a red moon, right? So we had a moon, and there was a red lining on around it. That was also because the light which was falling on the earth, which is much bigger than the moon, was getting scattered into the earth's atmosphere, and finally what reached us was only the red light
Wonderful.
which was around earth. Yeah.
Thank you, ma'am.
Yeah. Sir, you are not audible.
Piyush sir, unmute yourself and ask your question. I have one doubt, ma'am. Whether same theory is applicable for blue sea?
Yes.
Same.
Yes.
Same.
Yes. Same. Same.
Okay.
Same.
And lastly, all the participants are curious about the technology you used for teaching us. That last you tell and show us also.
Okay. Yeah.
Because
So,
this is very important in work from home, and all
yes.
physics teachers, lot of mathematics is involved.
Yes.
That is
So
a wonderful
actually,
technology.
yeah. That's the reason I took this, because I teach a course which is very mathematical in our department also, and I
Yes.
cannot make slides. So what I
Yes.
have, actually there are two ways. Either you have an iPad or something, so you can connect iPad to the internet, and you join Meet through that, and yeah, and there is a pen like this which can write on iPad. So
Okay.
it looks like this. I don't know.
Yes, yes,
Or
it is.
yeah, yeah. So in my department, what we have done is we have purchased few writing pads which can be connected to the computer, and which are around 5,000, 6,000 rupees. So department purchased them for us. We connect to our computer, and whatever we write on that can be displayed on the screen. So you can
Okay.
do that from college.
Which company, ma'am?
Uh, Actually, I don't recollect. I can share with you the link
Okay, okay.
from
I will
Amazon.
share with participants.
Yeah,
Yes.
please. I will immediately share with you.
Okay, ma'am. Okay.
Okay.
Thank you. Thank you for wonderful teaching.
Thank you,
Piyush
sir.
sir. Piyush sir, you had a question. I think he had lost the connection. Kshitija, Miss Kshitija, you had raised your
Yes,
hand. Ask
good
about.
afternoon, ma'am.
Good afternoon.
Uh, Thank you, ma'am, for this beautiful webinar. I have one question that what is the color of sun? When we look, it is a yellowish, but actually, when it is shining, it is a yellowish or not?
Actually, it has all the colors. So it is white, but what reaches us depending on again the scattering phenomena.
Yes.
So right?
Okay, ma'am.
Yeah, it's combination of all the colors.
Yes, white light. Yes.
Yeah.
So I think there are no hand raised.
Yeah.
I will propose vote of thanks. Uh, uh, Good afternoon, dear participants and Honorable Dr. Suwarna Datar ma'am. You have given a wonderful, thought-provoking lecture on blue sky and red sunset and sunrise. You have given initially your lecture started with live experimentation related to the water and some cloudy liquids, and mathematically starting from Maxwell's equations, you have showed us why the sky is blue and the sunrise and sunsets are red. Thank you, madam, for this nice, wonderful presentation and showing us the new technology of teaching, which can be utilized in work from home or this COVID-19 pandemic manner. Thank you, madam, on the behalf of myself, on the behalf of my college, Rajesh Shah Mahodaya Latur, and on the behalf of Atal Academy, Ministry of Education, New Delhi. I thank you for your wonderful talk, madam. Thank you, madam.
Thank you, sir. Thank you very much. Thank you for listening.